So Thorsten is very well known for his work on answer set programming. He has developed the clasp system, which is a very successful system, especially in his hands. Usually we use ASP on clasp and make a prototype and obtain pretty good results, but it's only when we send to Thorsten our code that it does improve and obtain really very good results, especially from what I know in inference of gene network from traces of activation of genes, for instance. He obtains very good results, and also in a competition on hard combinatorial problems. So, welcome, Thorsten.
Well, thank you for the introduction, and also thank you very much for the invitation to the conference. In particular, since I believe, and I think I will make this point later, that the community of answer set programming owes also an awful lot to the research that has been done in constraint processing. But I will come to this point later. So now that once I thought, now I'm free again. Good. So as you see, this is more or less also the theme of my talk, that I will be talking about that ASP is after all a Boolean constraint satisfaction paradigm, which is tailored to knowledge representation and reasoning. The outline of the talk is actually pretty classic in the sense that I will first of all try to motivate things, and here in this motivation I will actually at some point go a bit faster because we share more or less the same motivation in our community that you have here in CP. And then I actually decided to go a little bit in the foundations and talk about the motivations and also the definitions of ASP. It's funny that Toby couldn't make it this morning, because when I spent my sabbatical years back at NICTA, he always said, you guys with this negation, I don't understand this. And actually the point I'm trying to make today is that negation actually is classical. It's more or less the non-negated part of the program that is treated differently. Anyway, we'll see this in a sec. Then I will talk a little bit about modeling, and I included material about grounding, but I will not talk about this, but in this way, the material is nicely self-contained. And here in solving, I will become a bit technical, but technical in the sense that I will be talking a little bit about the architecture of clasp and how you can use it. And afterwards, I will do some public relation and advertise our project, Protasco, and wrap up. Okay, so motivation. Okay, here we go. So I think what we're all faced in computer science is we want to use a machine to solve problems. And what we do to this end is we map it on the computer, let it compute something, get an output, and solve it. And then, of course, we have these two possibilities. One is to deal with traditional programming, where we actually specify how to solve a problem. And actually, in German, we have this noun of Lösungsweg. And Lösungsweg is, if you translate it literally, solution path. So if you do programming, what you after all do, you specify a solution path. So you take the problem, you program, and then this program here tells more or less the computer how it can navigate to a solution, so to speak. And then the only thing the computer does in the end is only executing things. So what we do in declarative programming, and of course this includes, and it was pioneered in your domain, is that we do not do this. We do not somehow specify the solution path. We only specify somehow the rules of the game and the solution. So here we don't have a programming part, but a modeling part. And what is happening here is we just reformulate the original problem in let's say in a machine-readable way, in a formal way that a computer can understand it. And then we do search to find the solution. But no one has specified us actually how we find it. So this is then done by the machine. So the emphasis then really switches from the programmer, who more or less specifies how to navigate to a solution, to a system that does this fully automatically. I think this is I think in both of our areas exactly the same idea, just perhaps that of course the representation languages differ, and perhaps in ASP we are a bit more eager to get things completely declarative, but you'll see this in a second. Okay, so let's first give you an idea of ASP in a nutshell, and this way those of you who had too many drinks after the conference last night can relax a little bit. So ASP is such an approach to declarative problem solving, and well, now I can only claim this a little bit. It has a rich yet simple modeling language, which has just few basic constructs. And what confirms this a little bit is that the popularity of ASP actually is, what I observe is actually increasing more outside the area of computer science. There's people in biologists, for instance, start looking at this, or people that design games. Well, they somehow have a computer active, but they just write things down in ASP. And this actually, I think, is a confirmation somehow that things are actually simple. On the other hand, that's the second side of the coin. We have high-performance solving capacities that match the modern SAT solvers, and in this way, you can not only specify things in a very succinct way, but you can also execute things in a very fast, efficient way. So what I think where things start to change is where the community comes from. And so more or less ASP can say we have these four roots. One are deductive database systems, in particular since the modeling language contains first-order variables, and you remove them by instantiation. This is done by deductive database techniques. Then, of course, where the semantics comes from, logic programming with negation, but otherwise the community is deeply enrooted actually in knowledge representation and reasoning, and a lot of things are drawn actually from the area of non-monotonic reasoning. After all, the computational power draws a lot on constraint solving, Boolean constraints, and that was of course pioneered in the area of satisfiability testing and related areas like pseudo-Boolean solving and so on. So what you can do formally with it actually is that you can solve all problems in NP, but also one level higher in sigma pi 2 and pi 2, and you may wonder, why do you need this? And actually, the more you do applications, the more you find problems at this class, because often in applications, at least the ones we encounter, the problems are underdetermined. For instance, in bioinformatics, François was alluding to, sometimes there are 10,000, 50,000 different problems, different solutions, and then you want to, of course, to put on objective functions that select some of them. But often enough, objective functions that just count or sum up is not enough because they don't look at the structure. So you want something like inclusion to compare things, or Pareto efficiency and stuff like this. And once you do this, you go one level higher in the polynomial hierarchy, at least if you want to answer queries. The other thing that is for instance different in ASP with respect to SAT is because there is a first order modeling language that you have a uniform way of encoding. That you can nicely separate a program encoding from problem instances. And some of the problem encoding then works for all the instances, which you not get in SAT, for instance. So the other thing actually that feature of ASP is very versatile in the sense that it's not only good for ASP solving, you can use it nicely for SAT as well. We used it, the CASC is actually the first order competition where we used it for finite model generation. MISC is the Linux software update competition, PP is pseudo-Boolean, and of course SAT competition, and we more or less were lucky to win first prize at all these conferences. And as a result, of course, also ASP embraces more and more applications, well, not at the scale as you guys do, but it's interesting to see somehow how things evolve, because, and this is perhaps a bit of a personal remark, so when I was doing my PhD in the beginning of the 90s, I was doing this actually in non-monotonic reasoning, and this was still about Tweety and flying and things like this. So this community has really come quite away from really things that only worked on paper, with paper and pencil, and about capturing phenomenon. What is actually non-monotonic reasoning? How should this work? And now actually we have systems that play at this order of magnitude. The thing that I always had actually underestimate actually is the last thing, is this users thing. Because actually now if we have our software hosted at SourceForge, so it's potasco.sourceforge.org, and we have more than 30,000 downloads now. Of course people re-download versions and stuff like this, but there's still a community out there who's using it, and supporting it is not that easy actually. Okay, that's more or less ASP in a nutshell. Now how does this all was brought about? I think there was this shift in KR's paradigm, and KR as the field of knowledge representation and reasoning. So I did my PhD in a theory improving group with Wolfgang Biebel, and so we were completely into first order automated theory improving, and this was also how the field was dominated. So things, for instance, in Prolog or even in theory improving, you do a specification in first order logic, and then you pose a query, you find a proof, and more or less you extract from this proof, from the instantiation of the variable, your solution. And I still remember when Wolfgang came in and said, "Hey, these guys in Germany, they did the first SAT competition, and the automated theory improving community at this point was really, hey, they look at this as toys." So it wasn't taken serious. And then, however, of course, there was this big success of SAT, and there the approach is, of course, different, and you all know that, is that you provide a representation of the problem, and then it's not the proofs, but the assignment to variables, the logical model of the representation that gives you a solution. And the big credit for this definitely goes to Henry Kautz and Bart Selman, and I happened to be actually at this talk at ICA at the time, and that showed that you take planning problems, you represent them as propositional theories, then you take a SAT solver at the time, which was also the time of GSAT, so where stochastic methods came up, and then you look at the assignment that you get, and you extract the plan from it. And surprisingly, at the time, this was competitive with state-of-the-art planning systems, and this was a big shock to the community. How does that work? The other funny remark about this, talking to Henry at the time, actually they only did this to get benchmark problems. And the idea of how to encode planning problems actually traces back to Cook's paper on NP completeness, where he encoded the Turing machine. And they just took this way of encoding things and then encoded the planning problems. And you know all that this then went into automated software verification or hardware verification, and really has come a long way from Cook's original paper to bounded model checking, for instance. Anyway, just as an anecdote on the side, but this was somehow the type of a very, very positive earthquake that happened at the beginning of the 90s. And as a consequence, more or less, this meant that suddenly everything became constraint satisfaction. Because you have your problem, and what you look for is not a proof anymore, you look for an assignment. This was a big shift in way of looking at things. And then if you again, just switch your head and look at things, what was in the literature more or less, it was always the same. So you have here you have SAT, where you have propositional theories, you associate models. It's a CSP problem. You have non-monotonic reasoning, where you have order epistemic theories default. You associate expansions, extensions. Well, these are formulated in first order, but in the end, everything was done over a finite universe, so instantiated. So this was also nicely finite. And then, of course, here there's ASP. That's more or less the practical case of ASP, where you take programs and you associate stable models with it. So, in a way, this was the shift in paradigm, and more or less, that's actually what actually boosted also our research quite a bit. That we just looked at it from the perspective of CSP and not of automated theorem proving anymore. And if we now look a little bit at ASP, nowadays, actually, even though things started out from propositional programs, you can do this with propositional theories. You can do it with first order theories, even full first order theories, not over the not over a Herbert universe. But the important thing is actually this. These are not classical models; these are stable models. And actually, I will spend some time with you to get this idea to you what these guys really are and what the difference is. So this is ASP more or less in general. So pragmatically, what you deal with more or less, you have a modeling language. This modeling language these are first order programs, but the variables actually are taken over the set of terms. This set of terms may be infinite. You just have to make sure that you can transform this guy in a finite representation. Then you compute the propositional models, and you can afterwards interpret them as so-called Herbert models, that is, models over the ground atoms. So this is what ASP is more or less in practice. Okay, let's look at this a little bit closer to point out some difference just by getting some examples over. So looking at theory improving, let me just take Prolog, because I think many of you guys are familiar with this. So here's an example, and I've chosen this on purpose, and we will see this in the end. Let's say, I think you're familiar with the syntax, so we have two, let's say, blocks. A is on B, B is on C, and this is you can think of it also as a graph, and here you have a transitive relation, so you want to know when is a block above another one. And what you do then in Prolog, you do query answering, like theorem proving. So you ask a query, is A above C? Well, you can use this rule here, do a recursion, and you can derive it, and you can ask, is C above A? Then it says no. But what this does is more or less it tests entailment, and entailment means a query like this one is entailed by the program if it is true in all of the models. So the models somehow stay completely implicit here. You'd never look at them explicitly. If you say no here, this does not mean that of course it's false in all models. It just means there is at least one counter model. Okay, so models stay implicit here, even though they, of course, they provide the semantics to the syntactic operations. So Prolog, as well, is a programming language. That's also a point I want to make. Is so you want to exercise control if you write things down. And And that's completely fine. So if, in case, because the way you write things down, if you write it like this, left recursion or the termination condition first, your program will show another behavior. And so in this case, actually, control is not well implemented, and you will actually not be able to prove the whole thing. You all know this. This was actually one of the motivations why the stable models was invented, which then led to ASP, because one wanted to have a purely declarative approach to that. But anyway, I'm completely fine with this, because I think one has to get things right from the start. Do you want to have a programming language where you have to exercise control, or a modeling language? And Prolog is a programming language, and that's okay. Okay, now what about a model generation based approach like SAT? So we can write the same program in such a way here, and then more or less we have these three atoms here. We can replace all variables x, y systematically in this formula, and then look at the propositional models of it, the so-called Herber models. The first thing one has to say is that I'm always a bit surprised about if actually we give ASP code authentically, and then people say, oh, but you can do this in SAT as well. Yeah, but the thing is, this here is not in SAT. This is in LaTeX. So the important thing is someone still has to do a big job for you, has to translate a specification and put it in this format here. So in this way, someone has to do some programming. And you can't ride your bike into work and have 1 or 2 hours afterwards a new modelization running. Well, if you're a good C++ or Python programmer, of course. But you don't have a modeling thing here. That's something one often really forgets. And actually, I had a comment from a guy in hardware verification that starts to use ASP, and he said, oh, finally, he can make use of its PhD students. Because what often happens is people work 3 years on something, then they bury all the knowledge in the code. The next student arrives, he can't read the code anymore, so he more or less have to start from scratch. I think this modeling aspect, this transparency of the specification is really, really important. And that's what you don't have in SAT. And for the SAT people, again, I think this is completely okay, because this community is, in my opinion, driven by the success in computer-aided verification. And these guys have hardware description languages. They just want to compile their nice hardware description language that they standardized, have implemented into something, and then they use Dymex and run SAT stuff. That's perfectly fine. So this way, it's really where the community comes from, where there is a need to have a modeling language or not. So here there is no such modeling language, I think basically because there was no need for it, at the beginning at least. Okay, so what do we get here? Making this detour, closing this little detour, we look at a model, and the model I just denote now as a set of atoms where the atoms that are in the set are true. So this is, for instance, a so-called a Herber model. That is, all these guys are true in the model, and the false ones are not given. So if you look at it a little bit closer, I think we all accept this is what we expect more or less to be true in such a model. The facts, everything we can derive from the facts in the above relationship, and here this deduction here from this thing. But we also have these other guys here. So for instance, we have onBB. And so why do we have onBB? Well, because we don't say anything about onBB, so it's up to us to make it true or false. So it's not determined. So if in classical logic something is undefined, you can make it true and false. And of course, in this way, you get each thing that is undefined, you can make it true and false. You get all the combinatorics. So in this case, you get 426 models. And this is also an example that shows actually that the transitive closure that you have here, you cannot capture in such a language. Because you get all, of course you have to make true, to make true all the atoms that are derivable, like above AB, above BC, above AC, but there's no way that you can actually exclude this guy in an easy fashion. Of course you can do it with encoding tricks and stuff like this, but not in a natural way right from the specification. And we will actually see that this is one of the features that is obtained by the semantics in ASP. That's actually why I show you this example. Okay, so now let's position ASP in this. ASP is definitely a model generation based approach, which is rooted also among others in logic programming. Hence actually the program that we have seen before would work just as fine in ASP. It's more or less you have also these connectives here that denote implications and other language constructs. So if you push the button now and give this to an ASP solver, you get a model, and this is the model that you get. But the important thing, this is the only model and no others. And well, of course here this is a very, very easy case, and this is actually the smallest model because you have a set of definite clauses. But the reason actually why you only get one and no others is because it's not, so if something is undefined under this semantics, you cannot, then it is then this means you have no proof for it. And here you only accept models where everything that is true in a model also has a proof or a derivation for it. It has to be supported. And this is actually something that is, of course, started out in databases where with the notion of the closed world assumption. So if you don't have a tuple in a database, it's not unknown. You set it to false. And of course, this is a very efficient thing, because imagine if you had to print a timetable for a bus and you would have to list not only the times when bus goes, but also when buses don't go. It's a convention. So we say we do not list it, we leave the information open, it can be true or false, but then by convention we set it to false. And this saves us a lot of space. And of course the same is true in logic programming, where you have negation as failure, where you say, well, if it's open, if it's undefined, then I set it to false because I cannot prove it. And this is actually what makes on BB false here. So there is no proof. There is no proof for on BB or above BB, hence it is set to false. And this also gives you, in addition, this gives you a representational edge, even though, for instance, the decision problem in ASP as SAT basically is in NP. You cannot translate ASP into SAT in a modular way, but you can do it the other way around. Also, if you do not extend the language and you translate ASP into SAT, you risk an exponential blow-up. Well, if you do Zeithin transformation, after all, you keep it polynomial, but there is still a representational edge that you get from the semantics. Okay, so yeah, even of course this is just to make this point again, it's a declarative language, so if you change here the orderings, it will not change the semantics, it all stays the same. Good, so let's just wrap this up a little bit, these differences here. First of all, perhaps with respect to Prolog, there's of course this difference between model generation and query orientation. As a consequence, when you compute things, you have bottom-up evaluation and top-down evaluation. Here you have a modeling language where order doesn't matter the way you wrote things down, and here you have a programming language where you want to exercise control, that in the way you write things down, you influence how things are executed. So the rule-based format is the same, but then things start to diverge more. So of course here you have unification, while here you have instantiation. Of course instantiation is also a bottleneck of this approach, or more or less every approach that starts with the first order representation and ends up in a propositional representation. Let it be planning, let it be SAT, let it be ASP. But this is also, of course, something where one has to be very careful about. As a consequence, if you model, you also model in a different way. So here normally you use nested terms, while here you use rather flat terms. So just to give you an idea. So if you want to model an ordered collection of items, well, in Prolog you just take a list. But a list, after all, is a tree that goes deep. So it's actually a deeply nested term. Well, if you do the same in ASP, an ordered collection of items, you rather think of it as a table, or a spreadsheet, if you want, where you would say, well, okay, I have my items, and each item is a fact, and you describe, let's say, the item, and in a second argument, the position. So in this way, you have a table with two arities. One gives you the element, one gives you the position. So you really keep things flat. Of course, because the more you do with terms, the more difficult it gets to keep things finite in the end. So as a complexity result, well, of course, here we are Turing complete. Here as I mentioned, normally the standard case is NP. If you have disjunction in the head, you go one level higher. And now you may be surprised, why is there a Turing? Well, actually, since the language allows you to use unrestricted function symbols and in this way, then more or less the database techniques that you throw in at the beginning, they give you Turing power. So you can actually encode a Turing machine just via the instantiation procedure here. And the reason why this is the case, more or less, is if you model things, then you normally also always have a search aspect and you have a deterministic thing. You want to lay things out, to calculate things. And this is normally done in the instantiation phase. So, and hence you do not want to restrict the ground, because whenever you put a restriction, someone says, oh, I can handle that, take this restriction away. That's why at least we decided now we leave things open, and this way you have the full power here, more or less in the pre-processing phase. Good, if you compare things to SAT, it gets a bit more interesting, because they are of course very alike with respect to model generation and bottom-up techniques, but the first difference actually appears here, where here you use classical logic, and here you use a constructive logic. And constructive more or less means that it's not here in classical logic, you more or less have an interpretation, you look into the and you take this interpretation and evaluate your formula as you do in arithmetics. Well, here it's not enough that something is true in the interpretation, you also have to have a proof for it. This is why it is constructive. The good news is, so when you model things, you can just exempt certain atoms from that. You can say, well, you don't have to be proven, you can just be freely chosen, as in classical logic. Hence, you can here do closed as well as open world reasoning. But here you're of course committed to open world reasoning, because you can't suddenly somehow close things up. Okay, the next difference that I was already alluding to this is that here you don't have a modeling language, but here it's very important. Given that things are embedded in the area of knowledge representation, you have a modeling language that also allows you to model knowledge, as John McCarthy put it, in an elaboration-tolerant way. That is, if your world changes a little, then also your specification should change a little. This is very important. This is also what is a major criterion for the modeling language. The next thing is reasoning here. While in SAT you more or less concentrate on satisfiability testing, there are of course other communities like SMACSAT or PB solving, but these are a part where you look at other reasoning modes. In ASP, you really need things under the hood. You need it all more or less to cover the reasoning modes that you have in knowledge representation. So there's, of course, you can also check for models. But what is very important actually for us is enumeration, and enumeration in propositional space, so without solution recording actually. Projection is enumeration when you restrict the alphabet, where you say, okay, I only want to have solutions restricted to this alphabet, and you don't want to generate duplicates and stuff like this. Often enough, in particular in bioinformatics, people are interested in the intersection and the union, and the nice thing about this is, even though you may have an exponential number of models, you can do this with a linear number of calls internally to the solver. And for instance, bioinformatics, people sometimes ask, so they ask about the union because they want to know what is not in the union. Whatever is not in the union is irrelevant. They can discard it. And of course, what is in the intersection is really relevant because it belongs to honor. It must be true somehow. And so a common question that people ask, you use the optimization techniques, and you can ask, well, what is contained in the intersection of all optimal models? Or what is contained in the union in all optimal models? And here we can use multi-criteria optimization, and this way you can combine all these things in one setting. That makes it actually, I think, very nice that you have these complex reasoning modes. Okay, this about these contrasting this. So rooting everything is, as you see, you find these things. KR, of course, is the driving factor for the modeling language. The syntax is more or less from logic programming. Grounding uses database techniques. Here you have, I just put SAT there as a representative, but I will perhaps refine this a little bit later. And the stable model semantics with this idea of saying, well, if something is undefined, then you set it to false, is of course in all these areas, in database techniques, knowledge representation, normal reasoning notably, and logic programming. And this I think is nicely condensed in the stable model semantics. So if wrapping up this first part here is so ASP is a declarative modeling language, a declarative approach to problem solving, and I have to make this a bit more precise, but the important message is it's really tailored to knowledge representation and reasoning. So a lot of the features, a lot of the infrastructure that solvers have are really tailored to this end. And so if you want to make this a bit more precise, I think one thing in terms of declarativity that ASP has achieved, it does completely separate a program's representation from the algorithms used for solving it. So if you specify your problem, you do not know whether it's a MIP solver that solves it, whether you map it to integer linear programming, you map it to a SAT solver, you map it to a real ASP solver, or whatever. This is completely disconnected. You cannot pass anything behind a wall somehow. What you don't get for free, however, is, and I think this is obvious, is scalability. So it is very easy, I'd say, everybody who played with it, to come up with a specification that works. But to make it scalable is, of course, still something where one has to think about. And you have to think about combinatorics, but you don't think in terms of the implementation behind it. Think about what type of combinatorics does my problem induce? So if you only need a predicate with arity 2, why use a predicate with arity 5? You may have a problem afterwards because you introduce additional combinatorics. So, and this is something one has to get, of course, some experience in. So in a nutshell, somehow you have the ASP is this combination of these 4 types of techniques, and if you're a little bit more specific, actually, here at the end, you would you would say you could see it as an SMT techniques where you have several theories here. The first theory, of course, is you have to implement this constructiveness of the semantics. Then what you have in the language, you have weight constraints and cardinality constraints, which are a little bit more general than pseudo-Boolean constraints because they can appear everywhere in the program. They're not by they can also be false, for instance. Then there is optimization going on, the reasoning modes, and so on and so forth. So one way to view it is like such an SMT solver. Okay, now let me make things a little bit more precise. So first of all, let's look at the semantic idea. So the idea, so if we have here a propositional formula, these are the three classical models of it, and as I mentioned before, such a model is represent just such an assignment here with the true elements. So if you look at the formula, you actually only get one stable model, which is this guy. So it's a selection process. The stable models are among the classical models. But to find out actually how this works, let me change the format. Of course this works with arbitrary formulas, but let's translate this back to logic programming. So to get a better idea on that. So this is roughly the logic program that represents this formula here. And the important thing is, now that we have done this, we have committed to a format. So, and this format contains implication rules, and you can think of this as rules that produce something. And okay, you may think in terms of production systems now, but also if you look at intuitionistic logic, so with people that do not, for instance, that always want to have a proof for something to accept it, or that do not accept proof by contradiction, implication is the key operator. This is more or less how you form proofs. So, and then actually, if you look at these models here, like this guy or this guy, they make R true. But if you take this format, if you take the format serious, there's no way you can deduce R because there's no rule for it. There's no proof that uses implication. Okay, so this is actually why these guys are no models, because you cannot find a proof for them. So the first intuitive way to view what is a stable model, it's a classical model, but in addition, all the atoms in the model must be justified by some rule actually, and to make it more precise, there must be a proof for it in terms of implication. Actually, these ideas go back to intuitionistic logics introduced by Heiting and Gödel, like the logic actually the logic of here and there can be seen as the host language of all this, and this is Gödel's three-valued logic of this guy. But interestingly, this was discovered decades afterwards the stable model semantics came out. Okay, so it was not that one say, oh, we now want this logic framework, and then we make this precise. So with this proof again, I think the important thing to see here, if you have such a rule, that's what I was saying before with negation. The magic actually is not with negation. The magic is with the positive guy here. So if you want to evaluate this rule here, to evaluate the truth of not R, you simply look in the interpretation as you do in classical logic. In classical logic, you just evaluate. That's what you do here. You evaluate the negation just here. But for the positive part, evaluating it with respect to the interpretation is not enough. Here you actually want to have a proof, and for this actually you look in the program. Can you prove Q? And well, of course, here it's a trivial proof. Q you can prove from this guy here, then it's true. And of course, truth is then implied, but you want something stronger. And as a consequence, we've seen this before. For instance, you can easily, as a consequence, you can easily characterize reachability. This is by this constructive approach, and this gives you a representational edge. Okay, so let's make this a little bit more precise, but I don't want to go too much into details here, so that's why I'm speeding a bit now. So if we look at the most basic rule, this is a logic programming rule, and I think you've all seen this before in Prolog. This is the head, that's the body. These are the positive and the negative represented. And this tilde here, of course, I put this on purpose because it's not classical negation. And then a logic program is a finite set of rules, so it's not a list anymore like in Prolog, it's a set because order doesn't matter. And now to describe the semantics, again, what I was just saying is, if you have a truth table and you want to evaluate a classical formula, you evaluate the whole formula with respect to the interpretation at hand. What you do here is you only evaluate the negative part, and then for the positive part, for this guy you use actually for seeing what you can prove. And that's more or less the idea of the semantics. So you have this notion of a reduct, and this reduct only evaluates the negative part. So I just took the rule here now. So you only evaluate this part, And whenever some of the negative part is evaluated fine, then you keep this positive part here. So you stop here. You don't keep evaluating. And then you're interested in the smallest model of such a reduct here. And actually, look, this is actually a definite program. So a definite program has always a smallest model. And the reason why is the smallest model interesting? Because now think of it in a procedural way. The way you compute the smallest model is the iteration. You throw in the facts, then you look you look at all the rules that are applicable, then you throw in the heads of these rules, then you can keep going, you have a bottom-up approach, and once you reach a fixed point, this is the smallest model. But what is important is everything that you derive in that way is rooted in the facts. You can really prove it. And that's why this concept is interesting here, because then the definition of a stable model is just this here. So what you do is you evaluate the negative part, and that's where you stop. You don't evaluate the whole formula, and then you look, what can you prove from this? Because let's say by launching this bottom-up procedure that I just described, or by just computing it in other ways, and then if everything you can prove is in the model, is actually equal the model, then this is a stable model. That's the idea here. It's important that you prove things and that you make sure that everything that is in the model is provable, and that's the way you do it. You evaluate the negative part, look what you can prove from the rest, and if what you can prove is everything you can prove is in the model, you're fine. Okay, let's have a little example about that. So more or less, here we have some redundancy here, P if P, and of course a top-down approach would have problems here, and then we can derive P if we don't get Q, if we get Q if we don't have P. So looking at the truth table now, these are the four models that we have. And now the first thing we do is we compute the reduct semantically. So the reduct, of course, only looks at the negative part. We only evaluate the negative part. So here actually P is not in the model, so this rule remains. Here P is in the model, this rule is eliminated, and these are the two reducts we have. And now we look actually what can we prove from these guys, and here actually we can prove Q. Here we can't prove anything actually. And then the question is, what is stable now? And so the first guy actually is not stable, because we can prove more by making everything false. Here we cannot prove everything because we can't prove P here, so that's also not a stable model. Here we get a stable model, we can prove Q, and that's all we can prove, and so here we satisfy this, and here we don't give a stable model. So let's just contrast this with the classical case. If I just put here the classical negation, what would we get by going through the truth table? Again, what you would do is you simply, these are now the models, you get two more models. You simply take this model and you evaluate the whole formula. You actually don't care that here, in these two cases, P is true, but there is no proof following implications. Of course, in the proof system of classical logic, you have a proof, but it's not a proof somehow following implications and somehow respecting the format of the rules. Okay, so this was to give you a little idea on the semantics. So what you get as properties, you have of course no one or several models. Every stable model is a classical model, and I think one of the representational issues that you get already out of the semantics is the models form an anti-chain, in the sense that whenever you have two models, they can never be contained in each other. Good. So modeling. Actually, how am I doing this time? Left or gone? Okay, good. So modeling. So let me just go through this 15 minutes. The workflow briefly. So we model things, we write it as a logic program. This contains first order variables. We ground it, that is we remove the first order variables, we get a propositional representation. This is then fed into a solver, a propositional solver that spits out the stable models. And then the other thing that is actually important in this workflow, that there is a very short distance actually once you look at your stable models to modify the specification. This is, I think, one of the advantages of the approach, that it's very, very abstract, very high level. Let me just, here's just some language construct just to give you the flavor a little bit of it. So you have variables over the Herbert universe. So if you write this, this actually represents these three rules if we have these three constants. Here there is a notion of conditional literal, which you can, if you had a set, if you had this was included in the set, I think everybody could read it. You get QA, QB, QC, and just if there is no set, then you expand this as a conjunction. And this depends a bit on where it occurs, whether it occurs in the body or the head, how this is expanded. But it's a very nice thing because you have a type of quantification if you do not know how many elements you will have. So you can nicely, for instance, formulate a minimize on a symbolic ordering. You just say there is no element that is larger than this. Then you have disjunction in the head, and this actually is one of the constructs that takes you to the second level of the polynomial hierarchy. Then you have integrity constraints, so these conditions must not be true. You have choices, so you take at least 2 or at most 7 elements of the ground instance here, the elements here. Then you have other aggregates. This is just a short cut for a count. You have sum, average, etc. So let me just browse very quickly since time is passing through the workflow. So you have a problem. Let's say graph coloring. The first thing actually one has to think about, how does one represent such a graph? And again, keep in mind, here it's not about putting things into term structures. Here it's really of laying things out in more a table format. So you more or less have a table for the nodes with 1 argument, a table for the edges, 2 arguments, and that's it. So then you perhaps have a color, and then you think about what is the problem class, because that's how you encode the problem. And so this is, of course, you know, the graph coloring problem. And then if we rewrite this, we have these 2 constraints. So each node has to have a color, and we have to make sure that 2 connected nodes get not the same color. So if we express this in the logic program, and I give you now authentic code that you can right away feed into a solver. So this would be the nodes, 6 nodes. These are the edges of our graph. It's a directed graph that I use later for the traveling salesman. Then we have the coloring. So this is the problem instance. Normally you would have this in a separate file. And that's actually also the way we do CSP in the sugar-like or bee-like fashion. We take a CSP problem, we map everything down into facts, and then you write an encoding on top of it. So that's the typical way how you do it. Now for the graph coloring, the encoding that should work for each all problem instances. This is how you assign nodes colors to nodes. So the idea is you take a node, then you go over all the possible colors, and then you can color node X, let's say 3 with red, with blue, and with green. So afterwards you will have 3 elements in here once you have replaced the variables, but you have to make sure that only at least 1 and at most 1, so hence exactly 1 element is true. Hence you pick 1 element, you make sure that every node gets exactly 1 color. So if you just take this here, of course you forgot a constraint because you can still paint the whole graph in red or whatever. So you have to add the integrity constraint that says, oh, if 2 nodes are connected by an edge, they should not have the same color. This is an integrity constraint. Here you see you have an empty head. So this is the problem encoding. Normally this would be in a separate file. If I throw everything together in one file and call it graph LP, we can now look at the workflow. So what is happening now? The grounder takes over. So we input this in the grounder, minus text says it's now human readable format. So this is then what comes out, and you see there's quite some combinatorial explosion happening here. So this is the problem instance as we had it before. This is the grounding of the coloring. So this is actually coloring node 1 either with red, blue, or green, but you have to select 1. And this is what happens to the integrity constraint. Let's say we take edge 1 and 2. The 1 says 1 and 2 you cannot color both with red, or both with blue, or both with green. And this is the intermediate propositional formula again. And also here, the semantics has a drastic effect on the size of the grounding. Because once you know that that an atom does not occur in the head of any rule, you know that it can never be derivable. You can set it to false and engage simplifications. In a classical logic setting, you cannot do such simplifications. Okay, so also here the semantics helps a lot in keeping the grounding more succinct, while of course in the worst case this explodes. Okay, now then you feed this result into the solver. Here I took away the human readable format. I pipe it into clasp. If you give it a 0, it means give me all answer sets or all stable models. Here they are. And then you can, from this, you can just to close the loop, you can take such a stable model here, and you read off the solution of it. Another thing that is very, very helpful is actually that this approach keeps its symbols. So you have an encoding, even though you ground it, you have a symbol table, and you can really read things off. These are things that help a lot also in software engineering things around it, that you don't use the symbols. You don't have to care about the symbols yourself. So you don't have everything in integers. Okay, so concerning the methodology, actually the way is, how do you write this down? So you more or less follow a generate and test approach. So you write a generator, like here, you generate the colorings, and then you have a tester that tells you which of them are valid candidates. The generator, actually, you do not need in classical logic, because you just go through all the interpretations. Here you really have to make sure that things are provable. You only look at things that are provable. That's why you need this generator thing. So, and a logic program then is composed of normally of these four parts. You have the instance, you have a generator, a tester, and this may of course be mixed, and it's not a strict thing, and you may have objective functions in the end. Let's look at some examples here. First thing is set. So if I look at this formula here, and I want to encode it as set, that's the way I would do it. I have a choice rule. This means A, B, and C do not have to be proven anymore. They can just be chosen freely. So, and you don't have to choose anything. So if you just have this little piece of code here, it will generate all 8 interpretations, from the empty set to the set that contains all elements. And then you put this into conjunctive normal forms. These are then the negated clauses. This is the one implication, this is the other one, that's the equivalence here, and that makes sure that C must be true. C must be in the result. So these are integrity constraints, because you just impose a constraint, a selection on the generator here. Just to show this to you, what you can easily do, actually max that in such a way. For instance, if I add the negated implication here as weak constraints, and here I put some weights on top, you can run a max-out problem in that way. This is actually one way to describe an objective function, but we have explicit ways as well. So this is Queens. Queens is nice because this would be, let's say, the pedagogical way to write an ASP program. You have a generator, and then you have constraints. You rule out, you make sure that you put n queens, you make sure that none are on the same line, on the same row, and not on the same diagonals. But this actually is an encoding you come up quite easily just with this generate and test methodology, but it will not scale. And one of the reasons is the combination. Here you see you have 1, 2, 3, 4 variables, where luckily one of them is determined by the other 3. So this rule will produce a cubic number of ground instances. This is bad. Okay? So if you're a bit more familiar, you will use more aggregates. So this would be an encoding that someone a bit more experienced will come up with. You say here right away you put 1 queen in a row, 1 queen in a line, and here you have integrity constraints saying that you should not put 2 or more queens on a diagonal like this and on a diagonal like this. And this guy here will scale much better. So if you give my laptop is here, my laptop 1 hour, it will give you a solution for 5,000 queens with this encoding. So, which of course queens is not really representative from, just to give you a feeling for that. But just to tell you something that relates a bit more to CP. So it's very important actually in ASP that you can mix Boolean variables with non-Boolean variables. And actually right now we start working more and more on this, more or less with order encodings and this stuff. And so this is actually what you can feed this also in Gringo, and all the guys that are preceded right now with $1 are interpreted as constrained, either variables or constrained relations, and then you use some order encoding and compile them away, or you give them into G-code, or you give them into a dedicated solver. But anyway, you can also do this, and in this way you can mix things nicely on the encoding level as well. So this is traveling salesperson, and I think this is interesting because it has more or less all the features. This is again the tester, the generator, and the idea here is more or less you take a node, then you look at all outgoing edges, and among the outgoing edges you select exactly one, and this guy you put in the cycle. And the same here, you select a node and then you look at all the ingoing edges, and among them you select one edge and you put it in the cycle. So this is more or less your guess. So now what you did is you just guessed arbitrary incoming, outgoing edges. So now you want to make sure that you get a cycle. Well, this is just to select one node. It's just to show you this feature. Of course, this node, which is somehow minimal with respect to the systems order, is reached, and then everything that you reached and is in the solution is also reachable. And then to make sure that you really went through all the nodes, here you have an integrity constraint that says it must not be the case that there is one node that is not reachable. So in this way, you have to, talking generate and test, you really have to get a guess so that everything is reachable. And in the end, you have an objective function here, and this objective function minimizes the costs here, and actually it goes over the first element here, which you get out of a table which tells you which costs each edge have. The reason actually why you have here also x and y is because here you have a set semantics, and to make sure that you get multi-sets out, you also add the edge here, but what is really the summation here works on the cost function here. Okay, so I wanted to skip grounding, but now I don't have the... So let me briefly talk about solving, and notably about clasp. So how many minutes do you give me still? Was it 5? Okay. Good. So clasp actually, when we started with all this, we wanted to use Boolean constraint technology, but we didn't know really what is good for ASP and what. So we really started from scratch, and the important thing that we did is, and that actually really pays off, we didn't want to bury design decisions in Clasp. Clasp has a huge parameter space, and some of you may know that this year, to our surprise, it won this new SAT competition, where the idea is you ship in your system, and then each system is automatically configured. And then they run the automatically configured system. So it's not the tweaking of the developer anymore. And we won the crafted and the random competition. With the industrial one, I think we came in second or so. But it's really highly configurable. And the first thing you will need is, once you type class -- help, is a pager, because there are just so many options you can use. Anyway, so you see it has lots of options, but some of them are really specific to ASP, in particular dedicated treatment to binary and ternary no-goods, dedicated data structures for cardinality and weight constraints, and of course the unfounded set check, which gives you this, which gives you the semantics that everything is constructive. So Clasp has all these reasoning modes I was saying before. What is interesting for you guys actually may be that you can use it right away as an ASP solver, but also as a MaxSat or SAT solver, and as a PB solver. So it accepts OPB or VBO form. It more or less, it reads the first line and then it decides in which category it is, and if you want to use it as a MaxSat solver, you have to tell them that it has to optimize, and the same here with PB solving. So that's pretty nice actually for experiments if you want to compare different approaches with respect to modeling. You just take Clasp as a standard backend to that. So what Clasp does, it pursues a coarse-grained task parallel approach since version 2. It allows you to do parallel search, competitive search, and/or distributed search. But to be honest, the clear winner here is competing strategies. You have to do an awful lot of search space splitting techniques to come close to competitive search. And what you also get is you get different no-good exchange policies. So for instance, each thread you can configure individually what no-goods it should import and what no-goods it should export, and you can also configure somehow in which way they exchange the information, whether it's a hypercube, whether it's a complete graph, or I don't know what. Okay, so that's the architecture of Clasp, just to give you a bit more meat in that. Let's follow the workflow. You parse a logic program or Dymax or whatever you want to do. You do pre-processing, and here I think one of the important features is that Clasp here in the implication graph is shared between all the threads, and it contains binary and ternary no-goods. And in ASP this is really important, because typical ASP program has 70-80% binary clauses, due to cite-in translations happening at the beginning. The other thing is, of course, enumeration has to be supported, and we put a lot of effort in this, and otherwise Clasp as such, you have, I think one of the particular things about Clasp is the propagation engine that more or less uses unit propagation as far as possible. Then you can plug in post propagators. So this can be a constraint solver. This is actually the unfounded set engine. It can be a constraint solver there. We also use it here, as you see, for communication between the threads. And at that point, is actually many people use Clasp, like Minisat is used in the SAT community, who use Clasp to change things. Actually, want to here have actually a nice interface at that point here. So just to go a little bit through it, so help is actually one option that will give you a survey. Then what is important for the ASP community really is to be completely declarative. They do not want to bother about options of the solver. So one thing that we did, we came up with pre-configuration that one can use. And well, as you see, we are into acronyms, and Benny at one side, he looked just at web pages where you have English adjectives with a Y at the end. So let's just look at these on this Queen's example we had before. So I just did this on the laptop, so nothing really fancy here. So this is just taking the n queens encoding, the one I showed you, and with this number of queens here, and you see, for instance, that here this jumpy configuration on queens is very, very good. But for instance, the frumpy one is very bad. That's actually the worst one on this one. But this is actually the default of clasp. And the reason actually is that the idea is we are very, very conservative with options. So we do not turn any options on from which we know that they may have a catastrophic effect. A typical thing is set preprocessing, where you actually produce clauses. On some examples, this is disastrous. And so that's why we don't put it on. But of course, in many cases, it's really something that helps a lot. The other thing is here chatty, which also has a nice behavior. This is actually a default configuration that uses 4 different threads, and it comes pretty close to this configuration here. That's one thing. The next thing is the parallel mode, and as I mentioned, you can use, well, theoretically up to 64 threads. We sometimes go up to 16, because afterwards you get memory congestion problems, at least on the machines we have. You can configure things with complete and speed, and there are other options where you can configure the import-export things and whatever. So let's just look at some experiments, and so these are just benchmarks again against other systems. So the interesting thing why we've chosen them, so Plingeling exchanges only unit clauses, at least this version. Crypto-Minisat exchanges unit and binary clauses. Minisat has a very sophisticated way. They do it by load balancing, but more or less have a fixed architecture. And MiraXT exchanges everything. But just to give you an idea on whether there are differences, so we benchmarked this on SAT instances, but crafted category, and crafted is very much like ASP. So this is home ground for us. Okay, so this is a bit. So these examples, these benchmarks are actually nice indicator for ASP. And if you see here, this is the first thing one can see. This is now the single-threaded version of clasp. It's down here, and then first of all, one sees parallelism really pays off. So whenever actually the less dotted you get, so for instance, here's Plingeling, so you double the number of threads and you go higher. But there is no linear speed up. And actually on crafted instances, clasp actually shows a very, very nice performance. And this is due to the design as an ASP engine. So if you have combinatorial problems that are simpler, then clasp is the right engine to take. In industrial things, it's not the right one because for instance, we do not have special treatments for XORs, or we're not so aggressive in the way we restart, and so the setup is really different. But crafted is more or less our home ground, where clasp is particularly good. So coming back to this parallel mode, I think another thing that is really nice is, and I just show you now the default portfolio because it gives you the syntax. You can also write a file like this, where you just specify all your preferred configuration. This is the default configuration, and then what clasp does is you can fully customize it. It just assigns in a round-robin fashion, whenever you create a new thread, another configuration. And again, this really is, it doesn't give you the ultimate speed, but it gives you a lot of robustness. And this chatty configuration actually just used the 4 of them. Okay, so wrapping up. So we actually have all our systems gathered at SourceForge, and as you see here, there are lots of tools. So Gringo is actually our main grounder. Lingo and Pingo are design studies. So this is a design study in Python for Gringo 3. This is a design study in Haskell for Gringo 4. Then Clasp is of course our workhorse, but they are, for instance, unclasp uses unsatisfiable core-based optimization. And so Classfolio is a machine-based learning approach to get the best configuration. Clasp is an MPI-based version of Clasp where you can run over clusters. So we run it, I think, in Ireland actually. So we contribute a bit to Irish global warming and run it there at IBM on 4,000 nodes. So Klingo is a combination of the two, that you don't have to use Unix pipe anymore, because in ASP sometimes you have users that don't like the pipe. They want to have one system and do it. So, and here this is Rosso Klingo, ROS, some of you may know, ROS is the robot operating system. It's a robotics middleware, because we do a lot of robotics, because Klingo actually allows you to get sensor data in the solver. So the solver is running more or less, you use incremental solving techniques and grounding techniques, and then you get online data in to update your plan or whatever. And so one thing you may be interested in actually is our system aspartame. And some of you may, well, aspartame is an artificial sugar, but of course it has this nice ASP inside. That's something we did with the sugar guys in Kobe. It's more or less redoing sugar, but instead of doing it in Java, doing it in ASP. So more everything that is done in Java there, we did it in ASP. And which is of course in the way nice, because you can see how the constraints are encoded. You can read them, and you don't have to go into the Java code. Okay, and resource otherwise, we host actually a benchmark repository where ASP examples are collected. Then all the teaching material, also these slides here are there. And I believe in open source, and all these slides are also in LaTeX. So if you want to use them for teaching, just grab the LaTeX, include it in your teaching. We're all happy about that. And after all, if you want to enter a little bit more, we just finished a book just before Christmas last year, and this is also available here from the source. Okay, to ultimately wrap up, so I think ASP is an interesting thing, and it's really exciting. And keep in mind that I really started from wondering how to get Tweety flying, and what are the properties of non-monotonic reasoning, and this field of non-monotonic reasoning, which is now more or less finds itself in ASP, has come a long way. That's really, for me, this is really very, very, very nice that one finally gets things to run. I think the major advantage of ASP, and that's also I think why SAP people more or less use it for teaching, is the rapid application thing. So you're more or less, if you can use this modeling language also to model SAT things, because they are also, you can map things to SAT, back to SAT, but you can more or less, you can get in an hour or two, even if you're not so used to it, a working encoding of your problem. That goes very, very quickly. And so to sum up again with this thing, what is ASP? It's a combination of these four different techniques, where one here can more or less say it's a theory-based thing, and if you want to find more out of it, just go to our source. And here, well, that's it. Thank you very much.
Okay, thank you very much. We do have time for a few questions.
Yes.
An interesting talk. But I was wondering, when you model, you basically model backwards because you model in negation, right? Because your integrity constraints are negation, or at least you know how, compared to how we model in constraint programming. How hard is that? How good are people at negation?
At the beginning, people have to get used to it. But on the other hand, the reason actually why one has to keep in mind the notion of integrity constraint, as in databases, it's something you should not query. It is just there to guarantee certain properties, and that's why more or less it's natural here to have constraints that do not produce knowledge, because they have an empty head. And this is the technical reason why it's so people need some time, and sometimes it looks a bit awkward. I agree. If you want to say that there must be n elements, you have to say there are not. You do not put not elements. So this needs some time.
How are the function symbols being handled?
Pardon?
Function symbols.
Oh, you have more or less two types. So either you use them just as terms, and you do not uninterpreted function symbols. And other ones like arithmetic are either evaluated by the grounder, or if right now in the prototype, if they're preceded by $, they are interpreted by order encoding or by a constraint solver.
But what about is it dynamic?
Well, you have to make sure that you get a finite instantiation. So we allow function symbols, but the user has to make sure that you do not get an infinite representation.
So the grounder can get to you.
Yes, right. You have to. I think, I do this because I want to make some more difference, although this sounds a bit pathetic. But we just recently with Ansigel, we discovered a new genetic network for an algae that is little research. So this is actually where really biologists didn't put much effort, and we were able to recover the network to 7% accuracy with these tools. So that was very nice, actually.
Could you back up to where you had some of the URLs, the asparagus one? Thanks a lot. I don't have a question, I just wanted to copy it down.
Yeah. So, but you know, once you, actually when you Google Potasco, you'll get all this stuff. It took me a week to think about the acronym, and after 2 days it was Google's #1. Actually, we spent as much time in inventing acronyms and building systems.